Okay, so let me solve the first problem. So we are going to consider this PCA, silicon, sulfur, and gallium. So phosphorus and calcium, silicon, sulfur, and gallium. And they are interested in for you to understand, can you figure out the electron configuration? So you're just filling out S, P, D orbital and stuff in the right order. And then they want you to understand that, looking at the periodic table where they're located, can you see which atom is a lot bigger and which atom is smaller? And also the next one is an ionization energy. Ionization energy has something to do with how much energy do you need to take the electron out to the surface, right? So everything is bound to and has a lower than zero energy state. And how much energy do I need to take the first electron out so that make the electron and you can develop positive ion species. So I blow it up here. So first task is, I guess, let's find out where it is. So P is here, and calcium is here. Okay. So let me do the first one to the what is called electron configuration here. And what I can do is, okay, the P is, you find out the one that the closest noble gas, which is a neon. So I'm going to use a square bracket, neon, which is a 10 electron. And then you are going to have something that I underlined here. So that's 3s2, 3p3. So that's the answer for the one that I'm looking for. Can you guys do the same thing for the calcium? Let me try. You have to look for the calcium going backward. So you ended up seeing the argon here. So you're going to write argon. And then you're going to fill, okay, argon, and you have two more electron. That's in the, this is an N is 4. 4, yes. So that's the answer. Okay, so what's the next one? The silicon. Silicon, where are you? Here, right? Silicon's right here, which is a silicon, the closest, or the smaller number of electrons that corresponding to the noble gas is neon, and 2, 3, 4. So that will be 3s2. And the sulfur is down here. Sulfur, so once again, that is the neon. 3p, 1, 2, 3, 4. And the gallium is right here, number 31. So gallium. Going backward, you ended up seeing the argon. So argon. And then I am going to see, okay, argon, and then you need here, that's a 4s2. And you need the whole thing. That's a 3d10. And then 4. So that's it, right? This is pretty simple and easy, okay? I like to write this number down, 2, 10, 18. You know what I just wrote? That's the number of electrons in noble gases. We're talking about helium, neon, argon. it's good to know. Remember those numbers. And as you can see, there is a 2, 10, 18, and 10.
All right. Anybody else for 3 labs?
Last chance to submit.
Last chance.
Yeah.
All right. Just so you guys know, in the future, just so I'm not interrupting your lecture, if you put them in, hand them in right over there, then I'm less concerned. All right. So anybody else for 3 labs? Okay.
Okay, so the second question is a decreasing atomic radius. And so once again, let's find out phosphorus here, calcium is here, silicon is here, sulfur is here, and the gallium is here. So what do you see? We are talking about sizes. And what governs the size? Is size of principal quantum number. It's like an onion shell, right? The smaller the n. So this is when n is 1, n is 2, n is 3, n is 4. So they are in a different league. So I will, let's just see that. I'm going to put a different color, for example, here. These are the one that is going to be bigger than the one n is 3. So my choice is I'm going to pick this calcium and the gallium. They are the one who will be in the bigger side, right? The rest of 3 will be n principal quantum number 3, so which is smaller side. And then you want to kind of have an idea about, do you remember, probably many of the textbook has this kind of diagram shown up. So if you move from the left to right, the size of the atom is going to shrink. Why is that? Because you are increasing the positive charges in the center. Right? Nucleus, the bigger the atomic number for a given, I guess, onion shell, you have a much positive forces, so they're going to squeeze you the electrons toward the inside. Right? So that's why this one, which one will be smallest? Gallium will be smallest, and the calcium. So that one I know, and then I have to just put this other one, which is following my current notation. It will be silicon, phosphorus, and sulfur. So that's easy to think about that. And if you look at this, the size-wise, this is quite something interesting. The fluorine. Fluorine is probably the smallest if you do not count the hydrogen and helium, right? They are the smallest, and electrons are really, really tight. And the size-wise is very much tight or long. So that's why the fluorine chemistry is something very unique. Have you guys heard about Teflon? The cooking pan that one? Because the Teflon is made out of fluorine and the carbon. This is a polymer that's developed by DuPont scientists. And because everything is covered with the fluorine and the carbon is kind of bonding the fluorine together, they kind of stick themselves. They are very, very, what they call electronegative. So they really like the electron. So what that means is they don't like anything else. They just like themselves. So if you put the oil will just bounce around because they don't like, essentially Teflon do not like anything else. If you put the water, it will boil up, ball up, and then also if you put oil, it will ball up. So this has something to do with the size and how close you put the electrons to you. And I think the more fancier way is the electronegativity, which is in your reference table for your exam. There is actually electronegativity chart that you will use it later. And this is good. This is advanced class, so I think that this is just to refresh your memories. So this is now a little bit different beast now. We have to, I mean, it's the same atoms. So it was a calcium here and the gallium here, and it was silicon, phosphorus, and sulfur. So let's have a look at that. which one is easier? So when they say increasing the ionization energy that means it's more difficult to take the electrons out. Does it make sense, right? It's more deeply buried underneath it, so it takes more energy to ionize, so it's an increasing ionization energy. So I'd like to flip this question that which one has a smallest ionization energy? Which electron is the easiest to get rid of? The one that's hanging really far out, right? If you think about the planet, the easy planet to if somebody take it out is the one that's really far out. No, it's Neptune or Pluto, I forgot which one. But so which one do you think that will be the easiest one? That will be this, right? So now among these two are sort of the easiest electron to get rid of, or smallest ionization energy, because they are located far outside. And then now think about the situation that this is an electron in what orbital? S orbital, right? And this one is P orbital. So think about the S orbital is actually a spherical, okay? P orbital is more like dumbbell, right? So P orbital geometrically also they located outside as well. So among this, which one is easier? Gallium is easier than the one in the S shell, okay? So I think that I'm going to say the easiest one is gallium and the calcium. So that one I'm done. Let me switch back. So I figured that out. Gallium, calcium. Because this is in the p orbital, which is that's a 4p, and the electron from full s orbital, and that's why it's an easier to get rid of the electron bound to the gallium nucleus. So now we have looking at these three, which is these are the three, and this one needs some more thought on this. So let me highlight what electron we are talking about here. We are talking about 3p, and that's a 2. That's a 3p, 3. That's a 3p, 4. Right? So we are talking about same kind of shapes of electron, but this p orbital, one of them has 2 electrons, the other one is 3. The last one is 4. Right? So I am going to write this one. That's a 2 electron, 3 electron, 1, 2, 3, and 4. Right? So these are the sort of my picture that I can draw out. Talking about those are the one. Those are three scenarios. And then which one is easier to read? So among this, actually, which electron, I think the one that has a kind of similar idea, do you remember the D5 and D10? They are extra stabilization. So in here, do you see that this one is extra stable? So that one is the most difficult one to get rid of. Okay? So my next step is, okay, among these three, I am going to say which one? The P. P will be the highest one, and I just have to figure out silicon and the sulfur, which one which one is more difficult or easier to get rid of. Okay? So this one is how many positive charges? The same size of dumbbell, right? And this one is 16 plus. That's a 14 plus. So which one is more difficult? This will be more difficult than the other one. So that one is easier. The second easier, that one will be the most difficult one to get rid of. And that's the sequence that I'm getting. So the easier one is this one, the silicon. Then the sulfur goes there.
Could you explain again why phosphorus is the most difficult?
Yeah, so because of the, the p orbital has a 3 degenerate orbitals, and then when you have 3 electron evenly occupy each one of them, and the fancier way of saying is there's a magnetic coupling. It's all the magnets are all oriented together, so there is like a kind of nice interaction, secondary interaction between them. So because of this is all filled up. This is a sort of the similar situation. I give this analogy that if I have $1 million, well, if I have a $9,099 and he has $1, I'm more eager to take these electrons to make everything perfectly happy, right? So that's the one. They do not want to any changes because this is an extra stabilization that you will have. Just positive wise, this is will be easier, harder, and hardest. Just argument about the positive charge in the center, but this one will make it more difficult because of extra contribution from this. This is the same idea when you have something looks like here. It will be hard to get rid of the electron from here, right? But it is not actually. These 2 electrons will be taken out first. So mangan 2 plus is pretty easy to get. But if you want to have a mangan 3 plus, so now you have to break the symmetry. D5 symmetry, you have to break it. Same here, you have to break the symmetry of P3. This magnetic coupling is that the fancy way of saying it. Does it make sense? Okay, so it's when the electron goes in, you guys saw that when I put this one, I put 1 electron first because if they go to double up, that's not because there's an empty orbital. They want to go in, and they actually want to have the same spins, which is paired up this way. Okay, so I just want to. This is the same question. I just want to give you a recap on what can you explain what it is, and now this one makes sense to you. Okay, so essentially because of the N is 4, this is a recap, this is N is 3, and then this idea. Okay, so that's a size-wise, that's things that you can imagine. But ionization